Okay, so let's take a look at this question. So it says Linda goes to work 6 days a week. When it rains, the probability that she goes to work by train is 0.75. When it does not rain, the probability that she goes to work by train is 0.13. The probability that it rains on any given day is 0.4. So part A, on a randomly selected workday, find the probability that Linda goes to work by train. Okay, so part A here, and based on the given information, so this sounds like just a straight probability question that we can solve using a tree diagram. So in part A here, so I'm going to have to make a tree diagram. So basically we've got, first of all, it's either going to rain or it doesn't rain, right? So this is rain, doesn't rain. Now it says the probability that it rains on any given day is 0.4. So rain is 0.40. So not rain has to be 0.60, okay, for not rain. Now, it says that when it rains, she's either going to use the train or not use the train. So uses the train, right, doesn't use the train. So when it does not rain, right, uses the train, doesn't use the train. So it says when it rains, the probability that she goes to work by train is 75%. So when it rains, the probability of using the train is 75%. So not using the train would be 25%. Okay. When it does not rain, the probability that she goes to work by train is 13%. This is 0.13 when it does not rain. So this would have to be 0.87. Okay. Now we're trying to find part A here. Find the probability that Linda goes to work, by train. So first of all, you have to recognize that there's two ways for this to happen. She can go to work by train when it rains and then she uses the train, or when it doesn't rain and then she also still uses the train. So basically we're finding the probability when it rains and she uses the train, or when it does not rain and she's still using the train. Okay, so just multiplying these values here. So we've got 0.40 times 0.75 plus, so remember, or we should be adding values now. So not rain, so 0.60 times 0.13 for using the train. So if we calculate this, so using our Inspire, let's kind of just calculate the values. 0.40, 0.75, 0.40 times 0.75 plus, then we have 0.60 times 0.13. Alright, so let's make sure we type everything correctly. 0.40 times 0.75 plus 0.60 times 0.13. Alright, looks correct. So it looks like we get 0.378. So we get approximately 0.378. Right, this is our answer for part A. Okay, so part A here, probability by train is 0.378. This is our answer for part A. Okay, let's take a look at part B. Given. Okay, so as soon as you see the word given, that's a super hint that this is going to be a conditional probability. Okay, let me kind of erase this here so that I'll make room for part B. So part B now, given, so right away we know it's a conditional probability, that Linda went to work by train on Tuesday. Find the probability that it was raining. Okay, so we're trying to find the probability it was raining. We're trying to find the probability it was raining. Given, right, so remember this vertical line represents given, that Linda went to work by train on Tuesday. Given train. Okay, so remember whatever they say after the word, right after the word given, right, that goes after this vertical line here, meaning this is going to be your denominator when we're using the conditional probability formula. So as we recall, the conditional probability formula, the numerator is the probability of the intersection of these two. So rain intersect with train divided by the probability of train. Okay, remember this formula is in the formula book. No need to memorize it, but make sure you know how to use it. Now, the intersection, let me see, intersection of rain and train. So earlier we had the tree diagram, so we kind of have to go back to the tree diagram a little bit. So let me just kind of sketch it real quick. Remember, we had rain on any given day was 0.40. This is 0.60. And then when it rain and train, says rain and train. So when it rains, right, the probability that she goes to work by train is 0.75. This is 0.75. Okay, so this is the intersection right now, right? When she goes, right, where it rains, right, and she uses the train. So rains and uses the train. The probability of rain was 40%, and when it rains, the probability that she uses the train was 75%. Okay, so we have 0.40 times 0.75 divided by the probability of her using the train, which we calculated from part A. So that's one thing to keep in mind with these conditional probability questions. Sometimes, not all the time, but this denominator will be a value you've already calculated, or sometimes it might be the complement of a value you've already calculated, and you could just do 1 minus something. Okay, so keep in mind this denominator, a lot of times you might have already calculated this. Okay, so not all the time, but a lot of times you've already calculated this. So this was our answer from part A. So if we calculate this right here, 0.40 times 0.75. So we've got 0.40 times 0.75. Then on the bottom we've got 0.378, right? So that'll give us 0.793. So approximately 0.79365. Right. So once again, you can always round to 3 significant figures or just keep a lot of decimals. I usually just like to keep a lot of decimals just in case I need to use this value again later, right? I use the value with 5, 6 decimals. Okay, you should never use rounded values, right, to calculate something for another part of a problem or something, right? All right, so that was part B. All right, so we've got that was part B here, so we've got 0.79365. Okay, and then let's take a look at part C. Let me erase this real quick. So part C, it says, in a randomly chosen work week, find the probability that Linda goes to work by train exactly 4 times. Okay, so here's where it gets a little bit tricky in these multi-part questions. So right now, for part C, based on what they've asked, they've taken this situation and turned it into a binomial distribution type question. So you have to recognize that. So let's say capital X represents, right? So we're trying to find the probability that Linda goes to work by train, right? Goes to work by train. Goes to work by train. So we want to define our X, right? And then remember earlier in part A, we found the probability that Linda goes to work by train. That's 0.378. That's our success probability for this binomial distribution. So when we state this, well, X, right, is binomially distributed. Now, our number of trials, that's why earlier they gave you this. Linda goes to work 6 days a week. Okay, so in a randomly chosen work week, we know the number of trials is going to be 6. All right, 6, because there's 6 days that she goes to work. So that'll be 6. The success probability is this. This was the probability that she uses the train on any given day, right? So 0.378. So we have our binomial distribution parameters, right? And we're trying to calculate what she uses the train exactly 4 days. The probability X exactly 4 means X equals 4. Okay, so we're going to use a binomial PDF, and then we can type everything in. So menu, probability, distributions, binomial PDF. So trials is 6, success probability 0.378, and X value is 4. All right, so 0.11847. All right, so we had 6, comma 0.378, comma 4, and then our answer is 0.11847. 0.11847. So this is the answer for part C, 0.11847. Right. Kind of write that over a little bit. 0.11847. Now the last part, let's take a look at the last part, part D here. Oops, let me erase this. Okay, let's take a look at part D now. After n workdays, the probability that Linda goes to work by train at least once is greater than 0.86. Find the least value of n. Okay, so this is really important information right here, because basically what they're saying is the probability, right, of x greater than or equal to 1. Right, remember x represents Linda are going to work by train. They're saying greater than or at least once, greater than or equal to 1, all right, is greater than 0.86. All right. Now you think of the complement of this. So this represents 1 or more, right? So it could be 1, 2, 3, 4, 5, 6, and so on. Well, the complement of this is going to have to be, well, we know if x is equal to 0, right? Because x can't be negative. So if this already represents 1, 2, 3, 4, and so on, the complement of this is just going to be x equals 0. This has to be less than 0.14, right? Because these two values here have to add up to 1, right? Because probability adds up to 1. Okay, so now that we know this, we can set up a binomial equation, right? Now n, the number of trials, we don't know how many work days, right? Now the probability of success, remember going to work by train, that was 0.378, right? And then so failure is 1 minus 0.378, right? So we want this to be 0, right? So this would be 0 here. So this would have to be n minus 0, or just n. And we know this has to be less than 0.14. And basically we're solving for the number of trials n, right? So n choose 0. So anything choose 0 is really just 1, right? So anything to the 0 power is really just 1. So basically the left side here, we have, this is just going to be 1 minus 0.378 to the n power. I'm going to set this equal to 0, so then I'm going to minus the 0.14 to this side. This would be less than 0. And then we need to graph this, all right, to get our solution. So once I have this, I'm going to graph now. Okay, oops, I'm going to graph. So I am graphing 1 minus 0.378. So let me pull up a graph. So parentheses 1 minus 0.378 exponent x minus 0.14. So we're going to get a graph here, and then what we need is this x-intercept. So we need this x-intercept value right here. Okay, so let me kind of actually zoom in a little bit so see this a little bit better. So here we go. So we want to know when this is going to be less than 0. So 4.14, remember these represent days. So we have to go past 4 in order to be less than 0, because then you notice the graph is in the negative part here now. So you know n is going to equal 5. All right, so 4.14, so n is approximately 4.14, so n is going to equal 5. Okay, so that would be your solution there. All right.